While the function of the analog design tools might be fairly straightforward, it is important actually to put in some discipline to use them in a good way. Now, if we look at the schematic entry as a starting point, it's quite important that you use a good hierarchy. Now, the hierarchy should be functional, and it should also reflect what you're actually going to end up with in the layout. Now, for instance, it's not a very good idea to split the design of an operational amplifier up in two separate schematics if you can avoid that. It just makes it more difficult to understand what is happening, and this is one of the key points in doing good schematic entry, is that other people can understand what it is that you're designing. So if, for instance, we look at the cell schematic, it is important that you use physical components only. Now, if you're designing a simple amplifier, that could look maybe something like this, where we have 2 P transistors and 3 N transistors and power supplies and inputs and outputs. Now, another thing that's important then is to use good port names. So, for instance, this is an amplifier, we should have port names. This would be Vn minus, this would be Vn plus, this would be the output voltage, and this would be some kind of bias voltage. Now, this makes it a lot easier to use for a person who's using a schematic if you know what the inputs are used for and where the outputs are. Now, another thing that I strongly recommend is not to use global names, but to include the power rails in the ports. Thereby, you don't end up having a connection to a supply that you didn't know you have. So that could be VDD, and this could be ground here. Okay, so that could be all your ports on your schematic like that. Okay. Now, it is sometimes tempting to put in voltage sources to test your device, but it's something that should never be done. And the reason is that once you want to use this device somewhere else, then you need to rip out the voltage sources, and that is something that can easily cause errors. So what you need to do when you have your schematic is that you need to then also have a good symbol for the schematic, which looks like it should be looking. Now, so this is what we have is an amplifier, so it should look like an amplifier, something like this. And we need to put in the port names as well, like so. Now, for instance, and this is something that you do see, is that people swap the plus and minus, for instance, and then that's only not a very good symbol any longer, because when you use it, you think the one with the minus is a negative input, and when you do a feedback, then you take it from the output to the negative input, and if the symbol is not correct, then you end up having something that doesn't work and you don't understand what's happening. So it's really important to put in some diligence. It takes you a little bit of extra time, but the time that is saved overall is very often quite big. Now, once you have done your layout, or sort of your schematic, and you have done your symbol, you need to test it, and for that you make a special circuit diagram, which is your test bench. And in your test bench is where you have test sources and what else you have. So for instance, your test bench could look something like this, where we have a power supply being applied to the supply input, we have a voltage source being supplied to the positive, we have coupled it as a voltage follower. And now I suddenly discovered that I have made a terrible symbol because I completely forgot to put in the bias voltage. So this was an example of how not to do it. Let's just quickly rectify that. A bias voltage on the symbol, and that also then appears in the test bench, like so, where we have applied a bias voltage to the amplifier. You you can probably draw that schematic better than I did there. Now, probably a special mention is current sources. Now, current sources unfortunately have the nasty habit of making the simulations seem really strange, and for that reason I very strongly recommend the current sources are only ever used as inputs to current mirrors, like this, where we have a current source here that is fed to the input side of the current mirror, and that current should go out here. So this is the one you use in your circuit rather than the current source, because that will almost certainly cause strange behavior at some point in the simulations. Now, when we look at the layout, there's a few things that is worth mentioning. Now, if you look at a cell in the first instance, so laying out, your amplifier or your NAND gate or something, it is possible that you have the opportunity to use what's called P-cells. Now, essentially, P-cells is a little bit of layout that is done automatically for you. Typically, it's just a transistors with all the layers. So this is quite typical to have in the design kits. Now, another thing in the cell layout that is important to look out for is matching of transistors. Now, in many analog functions, you do rely on transistor matching. For instance, a differential pair in an op-amp, and by doing the layout so that it is nice and symmetrical, you can get much better matching performance than if you just lay out the transistors in a random fashion. You should of course also pay attention to how big the cell gets, but that is often taken as a given. Now, another thing to think about is how to distribute global signals. Now, signals for that is, for instance, power. Your power signals, you need to have the wires being wide enough to carry the amount of current that you expect to have in that particular wire. Now, typically there will be design rules for that, saying that you're allowed to have, for instance, 1 milliamp per micron width of current in a wire. But that depends on the design rules. This also depends on which metal layers that you are talking about. Now, also what is important is to think about clock distribution. Now, distributing clock is something that is really important, so that the clock arrives at the same time at all the gates. Also, what is important is that it doesn't interfere with sensitive signals. Now, you don't want to route the clock, for instance, over a very sensitive amplifier input or some sensitive reference, because that would likely cause EMI issues, and that would break the chip or cause it not to work properly. Likewise, the clock is also the distribution of references. You might have a voltage reference that you want to distribute to a number of sub-circuit, and you need to make sure that that voltage reference doesn't pick up noise along the way. So you might think of doing things like shielding and other ways to protect the reference. Now, when it comes to getting off the chip, you have the pad ring. So usually the pads or the connections to the package is arranged at the perimeter of the chip, since this is the only way you can really bond to it in most package technologies. And in the pad ring is normally where you think about any I/O buffering that you need to have there. The reason is that off-chip capacitances are much bigger, or impedances, generally speaking, is much lower off-chip than it is on-chip, so you might need to think about beefing off your signals so they can actually be transported off-chip. The other thing that's really important in the pad ring is to have sufficient electrostatic discharge protection so that the chip doesn't blow up if it's been touched, or even in manufacturing. Now, the important signals, as said before, are things like the power signals, the clock signals, any high-speed and sensitive signals is what you should be routed first. But other than that, there's other things to think about when routing blocks together. Now, in addition to the power, all other tracks you should consider the wire layers that you route in, because that might make it more easy or less easy to do. And you should also consider the width of the tracks so that they have low enough resistance and can handle the current that they have. Another important part is the port placement, because when you place the ports, that will then dictate how you can route to a cell. So that can be more or less easy to then do this subsequent intercell routing if you have placed the port in a good way. Now, one way to do the placement, for instance, if you have a cell here and you have ports, then you can place ports at the boundary of the cell so you don't route over the cell, because then you can route between cells in the same metal layer, for instance metal 1, as you use inside the cells. You should probably also save some of the metal layers so you can route across the cells. So let's say you have metal 1 being port in that direction. You can have metal 2 being ports at the top and bottom of the cell. This is typical, like so. And then if you have another cell, you can route them up. So some of the wires can maybe connected directly in metal 1 like that, or you might need to have something that connects to another metal somewhere else, but then you can do maybe like this, where you have metal 2 going vertical and metal 1 going horizontal, and you can route them up like so. And as I said, good idea to save a metal layer that you can route over the cell like this. So for instance, this could be metal 3 and there's no metal 3 inside here, which means that you can route metal 3 across the cell in case you need to go that way around. As with this schematic entry, there's a few points of note for these circuit simulations that you should carry out when designing a chip. Now, the first one is a functional simulation. The purpose of the simulation is to verify that the circuit is performing the function it has been designed for. So you need to set up a certain number of metrics so you can verify that your circuit meets the specifications. Now, in doing so, it is actually very, very important that you simulate over as many variations as you can think of. Now, the reason is that the manufacturing processes they have large tolerances. So sometimes they will make transistors which has lower capacitance than other times. So you really need to make sure that you simulate over all possible simulation corners. Now the corners include process variation, it includes temperature, it includes power supply voltages, it also includes any sort of reference variations that might be a matter to you. If you have a voltage reference and it's important that that has an exact value, you should first find out what is the variation that you can expect from that, and then make sure that your circuit works over all possible variations of that. So the voltage reference, maybe there's a frequency reference, maybe there's a current reference, maybe you have other references that matters to you. Now the first three goes typically by the name of process voltage temperature, or PVT, which is standard, and you always have that in both analog and digital circuits that you should simulate. When you do analog circuits and you have devices that relies on matching, It is also really important that you simulate the matching property. And the best way to do that is use Monte Carlo simulations. Now, Monte Carlo simulations add a random variation to the process parameters that it has been programmed to, and then you run a simulation, it adds a new random variation, you run another simulation, and so forth. So this is the most efficient way to explore a large number of parameters that can vary, and that is normally the case for a chip. You might need to run 30 or 100 simulations to have a reasonable statistics to see how your circuit vary under matching conditions, but this is necessary, for instance, to determine the offset error of an op-amp, which by design should be very close to zero, and most of the actual offset error comes due to random variations. And the last key simulation is on an extracted netlist, so you can see how the parasitics influence your circuit. A few things about the corner simulations, and the reason it's called corner simulations is best understood if you look at say P and N transistors and just look at one of their parameters. Let's say the current gain of the transistors. So if we have a 2D space here where we have the N transistor current factor mu Cox, and on the x-axis and on the y-axis we have the P transistor current factor, then the N transistor current factor is going to be varying between some values. The minimum value we can have for the N and the maximum value we can have for the N. And the P transistor is likewise going to vary from some minimum value we have for the P and some maximum value here for the P current factor. So if you plot it in this two-dimensional space, if we have two transistors, an N and a P, then the current factor for both of them is going to sit somewhere in this rectangle. Now you can imagine that if we have more than one parameter, we also have the threshold voltage, we have maybe the minimum channel length, we have all sort of different parameters in the transistor. We have a highly dimensional space, but it's going to be some kind of rectangle in a high dimensional space. Now the typical value is normally the nominal point here. So this is the expected value for both the N and the P current factor. However, it is unlikely that the chip you manufacture are actually going to have that value. So in case that both the current factors for the N and the P, they are high, in which case you sit up in that corner there. It's corner because it's the corner of a multidimensional rectangle. If they draw more current, that means that the circuit would run faster. So this is the fast corner. Now at the other extreme, if both of them are at the minimum value, we have the slow corner sitting down there. The two other corners don't really have a standard name. They are important because in some circuits it's important that the P and the N transistors don't become too different. My preference is calling this corner here the up corner, because if you have an inverter, the P transistor sits on the top pulling up, so it would be stronger pulling up than pulling down. And likewise, I call this one here the down corner, like that, with a fast N and a slow P. So these are the corners that you have to simulate. Now, in principle, you need to have all the permutation of different temperatures, different power supply voltages, different references, different process corners, and so forth to simulate them all. That can be a bit too much, so sometimes it might be better to say, make the assumption that at hot temperatures, it's likely that the transistors are slow, so we simulate hot temperatures in the slow corner to get an extra slow corner, and so forth. Now, if you have more than just transistors, you should also include these other components in your corner simulations. For instance, resistors, capacitors, and other components you might have. Now, you can build them into the fast and slow corners if, for instance, you have large resistance that tends to slow down the circuit, if you have large capacitors that tend to slow down the circuit, so you can look at the upper value of those and include them in the slow corner. And likewise, if you have small value for the resistors and small value for the capacitors, that would sit in the fast corner. Now, a quick look at the extraction tool. If, for instance, we have a layout of a cell like this, where we have the layout of an AND gate. So here we have two N transistors in series. We have the output being connected up here with two P transistors in parallel. I haven't put down the welds and the select layers. And we have power supply and we have ground like that. Now, when we do the extraction for verification, we would then ask the tool to extract the component that we have in the schematic. So that is probably going to be a P transistor that sits here, with the gate being connected to the poly, the source being connected to this supply, the drain being connected to the output. We got another P transistor, and we have two N transistors, like so, and then we have the interconnections. So, and with that we can do the layer versus schematic verification. Now, as explained earlier, we also might want to do parasitic extraction, and then we can see what sort of parasitics that are in the schematic as well, or in the layout, and then we can do more detailed simulation. Now, for instance, you'll see that the output node here and this input node here, they cross, so that means that they're going to be a small capacitance between these two nodes. So this is a sort of parasitics that is going to be automatically extracted. Another parasitic that is probably going to happen is that there is a large piece of metal here and that sits over the substrate, which means that there's going to be a capacitance from the output node here on this metal node down to the substrate. Likewise, there's probably going to be capacitances from these gate electrodes that runs over the substrate down to the substrate for both of them. Other parasitics being extracted are typically resistors. Now, you might have a long wire here, which means that there's going to be some kind of series resistance in that. You might also have series resistance here in the gates, and you might have series resistance maybe in the other long track up there. Now, you can really have a huge amount of parasitics that are in there. So usually for the parasitic extraction, you would normally set a threshold below which you will not actually extract them, because the net list becomes too big. Now, once you've done your extraction, you can do your post layout simulations from that.